video, we're going to talk about logarithms. Our learning targets are going to be not this. We're going to evaluate a logarithm using technology, and we're going to rewrite exponential equations as their corresponding logarithmic equations and vice versa. We're going to start with this warm-up problem. So, a few months ago, Kanye West was admitted to San Mateo Medical Center for unexplained symptoms. The patient exhibited weird behavior that no one had ever seen before. Doctors had no idea where to begin with treatment. Mr. West, someone whose favorite hobbies include rapping, monologuing, and interrupting people, has unfortunately completely lost his ability to talk, leaving only his ability to communicate with animalistic gurgles and primal screeching. His eyesight seems to be impaired because he's been spending most of his free time repeatedly walking into walls. Yesterday he tried to eat his family, and he hasn't had a pulse since February. Some doctors were concerned that this was the beginning of the zombie apocalypse. Others didn't care because they don't keep up with the Kardashians. Unfortunately, some doctors were right, and it is the zombie apocalypse. Despite California's best doctors and security being on the case, West has managed to infect multiple people today, bringing the zombie count up to 10. Based on extensive research on these Walking Dead via popular TV shows and movies, we predict that each zombie will spread its disease to 10 other people per day. At this rate, how many days from yesterday until the entire population is infected? Given the world population is 100 billion, it's not 100 billion, but we're going to pretend that it is for this problem. So we're going to fill in this table. We have the number of days that have passed by. I'm sorry for my squeaky chair. We have the number of days that have passed by on the left since yesterday, and the number of zombies that we have, or the zombie population. When 0 days have passed by, we have one zombie only, and that is Kanye West. When 1 day has passed by, we have 10 zombies. That's said it in the problem. If 2 days have passed by, these 10 people are going to infect another 10 people. So we're going to have 10 times 10 zombies, or 100 zombies. For 3 days passing by, we're going to have 100, or 10 times 10, times 10 zombies. So that's going to be 1,000 zombies. On day 4, we're going to have 1,000 times 10, because all those 1,000 people are going to infect another 10 people each. So we're going to have 10 times 10 times 10 times 10, so we could see a pattern. That's why I'm doing that, that's going to give us 10,000. Instead of writing out all of these 10s, I'm going to just find what my pattern is. Well, on day 1, I had 10 to the first 10 multiplied 1 time. On day 2, I had 10 multiplied 2 times. On day 3, after 3 days, I had 10 3 times, and 4 10s on the 4th day. So on the 5th day, I'm going to have 10 to the 5th power, which is 100,000. On the 6th day, I'm going to have 10 to the 6th power, which is 1,000,000. I'm just going to write 1 mil. On the 7th day, I'm going to have 10 to the 7th power, which is 10 million. On the 8th day, 10 to the 8th power, which is 100 million. And the 9th day, 10 to the 9th power is going to be 1 billion. And I'm still haven't reached this number, so I have to keep going. On the 10th day, I have 10 to the 10th power, which is 10 billion. And on the 11th day, because I still haven't reached my number, I'm going to have 100 billion, and that's where I stop because I found my answer. This is my answer. 100 billion is what I was, 100 billion is what I was looking for. So how many days did it take before the entire population was infected? We found it's 11 days. It's 11 days that it took. It's kind of crazy how fast that was, because it's pretty realistic that each zombie would infect 10 people per day. What is the pattern for this table? So we already found it. We found that to find the population, we always use that formula, y is equal to a times b to the x power, right? In this case, our a is 1 because it's just Kanye West by himself. So we have y is equal to b to the x power. In this case, our b, or our growth rate, every time we're multiplying by 10. So the function that we found, we could do it that way, or we could have just looked at what we had. Our output, our population, was 10 to the however many number of days we had, 10 to the x power. X represented, like this says here, the number of days that have passed by. And y represents the number of zombies that we have. So the number of zombies, or the population. And we always know that our output is going to be our population. And our x is going to represent some time that has passed by, and in this case it's days, for exponential functions. How did we figure this out? Well, we went through this whole list to figure it out. And that's a lot of work. Maybe it wasn't for this problem. It wasn't too much work for this problem because it was only we only had to do up to 11 days. But if we had a weirder number, like, or we had too big of a number to count to, it would be really difficult to figure out. But how we figured this out is we raised 10 to different powers, different increasing powers. I'm going to say exponents instead of powers, until we got 100 billion. But what if we did this problem using the actual population of the world, which is 7 billion, and I wanted to know exactly how much time it would take before the population was infected? Could we have done it in the same way? Could we have gone through this table to figure out for 7 billion? No, we couldn't have, because we only see powers of 10. 7 billion is not a power of 10. So no, we can't. But we do know where it's in between. We don't know exactly how much time it would take to infect the entire world, but we do know it's between 9 and 10 days. We know it's in between 9 and 10 days because 7 billion falls somewhere here, in between 1 billion and 10 billion. So no, we know that it would take between 9 and 10 days. But we don't know the exact time. So we don't know the exact time. There is a way that we can figure it out, though. We can estimate, but there is a way we can find out exactly how much time it would take. And we're going to build up to that. So the rule we came up with for the warm-up is written in exponential form. We talked about that. In that rule, the input would be the number of days. The input is the number of days for that function that we came up with. So it's the number of days, which is our time, which is what our input always is for exponential functions. And the output, so the output would be the number of zombies, or the population. It's the number of zombies, or the population. That's always our output for an exponential function. But for a problem like the warm-up problem, we want our input to actually be 100 billion, and 100 billion represented the number of zombies, or the population. So we actually wanted our input to be the number of zombies. We wanted our input to be the number of zombies, or the population. And we wanted our output to be the number of days. We wanted the output to be the number of days or time. So we want to flip our output and our input. We want to flip our inputs and our outputs. We've done this before. We've done this before by finding the inverse. So we're going to find the inverse of that exponential function. We're going to find the inverse, and that's going to help us find a function to use where we can plug in any population and find how long it would take to infect that population. So we could plug in the population and it would spit out the number of days. If our original function for this problem, the exponential form is y is equal to 10 to the x power, which is what we came up with up here, then to get our inverse, and I just left that blank so you wouldn't know what word I was going to say, then to get our inverse, we have to, the first thing we do to find our inverse, if you remember, is we flip our x and y values. So we flip x and y. We flip them. And so from here, if we flip our x and y, we're going to have the equation x is equal to 10 to the y power. The next thing that we have to do is get y by itself, solve for y, because y is our output. We need for functions our output by itself. So we're going to solve for y. How do I do that? How do I get y by itself when it's in the exponent? I have no idea. Well, I know, but you don't know yet. We don't know. We don't know yet. We don't know how to do that yet. So we can't, not in a way that we've seen before in this class. We can't take a root of each side because the exponent isn't a constant. It's not 10 to the second power or 10 to the third power. We can't take a specific root if we don't know what power we were raising the initial function to. So because it was a constant, it's an unknown exponent, so we can't take the root of an unknown. We don't know what root we would be taking. That exponent is a variable, so it causes a problem. We can't divide, multiply, add, or subtract something on both sides to get that y by itself. So we're stuck. And a long, long time ago, mathematicians were having the same problem. So they needed a way to reverse exponential functions, and they created these things called logarithms. So this is what a logarithm is and where we use it. It is the inverse of an exponential function. Okay. So inverse functions are those that undo each other. Just to remind you what an inverse actually is. The opposite of multiplication, or the inverse of multiplication, would be division. The inverse of addition would be subtraction. And the inverse of an exponential, exponentials, is logarithms. Okay, so let's do some examples of inverses with graphs. This first problem here, we have y is equal to x plus 5. And we also have y is equal to x minus 5. These two things are clearly inverses of each other. I'm doing the opposite thing to that input value. In one, I'm adding 5 to the input, and in the other, I'm subtracting 5. Those are opposites. These are inverses of each other, and we're going to see that when we graph them. For y is equal to x plus 5, I'm going to pick values for x to plug in and see what I get for y. I'm going to plug in -1, I'll get 4. I'm going to plug in 0, I'll get 5. And I'm going to plug in 1, and I'll get 6. I'll plot those points, -1, 4, 0, 5, 1, 6, and I'm going to connect them. I know this is a straight line, so it's just going in a straight line. For my inverse, y is equal to x minus 5, I could pick values for x to plug in, see what I get for y. But what I know about inverses, since I already have this table here, I don't need to calculate anything. I know this is the inverse, so I can just flip my x and y values in that first table. And I can check that that's true, just to make sure these are inverses of each other. If I flip -1, 4, I'd have 4, -1. Well, if I plug in 4 to this equation here, I would have 4 minus 5, which is -1. And yes, this is, or these 2 points are flipped, because they're inverses of each other. If I focus on this point here, I would have 5, 0. Does that make sense? If I plug in 5 for x, yeah, I would get 0 for y. For the last point, 1, 6, I would have 6, 1, and if I plug in 6 for x, yeah, I would get 1 for y. I'm going to plug in 4, -1, 5, 0, and 6, 1, and then I'm going to connect them. And what I'm going to see is, if I drew straighter lines, something that you should remember from those inverses, that inverse unit we had, is that when I graph the inverses, they're going to be a reflection over the line y is equal to x. So they should look like a reflection over that line y is equal to x. Inverses, and they are that in this case. I want you to try this one on your own. Try graphing those two on your own. Remember that multiplying x by 5 is the opposite of dividing by 5, which is the same as multiplying by 1/5. Those are opposites of each other, so your graphs should look like inverses. For now, I want to talk about exponentials. So you could pause the video and do this problem while it's fresh in your head, and then I'm going to move on to this. So I want to do with exponential functions. I have y is equal to 2 to the x power. I don't know what the inverse equation looks like to that yet, but I want to graph it based on the fact that I can flip my x and y values. So I have y is equal to 2 to the x power. We've done this a million times already. For exponential functions, I have -1 and 1/2, I have 0 and 1, and I have 1 and 2. To find the inverse, I don't know what the equation looks like yet, but I do know what the table looks like. It's going to be 1/2, -1, 1 and 0, and 2 and 1. I just flipped this point. I just reversed the x and the y's. I did that for all of the points. I'm going to plot my red points. I have -1, 1/2. I have 0, 1, and I have 1, 2. I'm going to make sure I don't touch this horizontal asymptote. I know there's no vertical change, so my horizontal asymptote is going to be y is equal to 0, and that's going to be my graph. So I know the horizontal asymptote is y is equal to 0. The domain is negative infinity to positive infinity. The range is 0 to infinity. For this other table that I have in blue, the inverse is going to be, I have 1/2 and -1. I have 1 and 0. I have 2 and 1. And when I connect these, I'm going to make sure I don't touch, instead of not touching y is equal to 0, since everything is flipping, so since all of my x and y's are flipping, instead of my asymptote being a horizontal line at y is equal to 0, it's actually going to be a vertical line at x is equal to 0. So instead of y is equal to 0, I'm going to have a vertical asymptote at x is equal to 0. I just flipped my x and y and my x. So when I connect these points, I'm going to make sure I don't touch that line. And as you can see, I'm not like perfect, but and that's not also. This is a reflection over that line. These are a reflection over the line y is equal to x. It's a reflection over that line, those two inverses. I'm sorry, the domain for the blue function, and that's a logarithm function. It's the inverse of an exponential, is 0 to infinity. I'm going from 0 to infinity. Those are my included x values. For my y values that are included, it's negative infinity to positive infinity. All y values are included for my logarithm function that I graphed in blue. What I notice, and what you should notice about all of these, is that your domain and your domain in the original is actually your range in the inverse, and your range in the original is actually your domain in the inverse. This is going to always be true about a function and its inverse. The x and y values are all flipping, so it makes sense that all included x and y values would flip. Those are the important things to take away from the graphs of inverses. Just to clarify, how does I want you to try this one on your own. So try graphing this and its inverse on your own. How does the asymptote change when graphing the inverse of the last two? We talked about this, the horizontal asymptote. So the horizontal asymptote, and I'm sorry, it's the last two because you're supposed to do this one and you'd see the same thing. The horizontal asymptote becomes the vertical asymptote. So the horizontal asymptote becomes the vertical asymptote. Instead of having a horizontal asymptote for the exponential function, for a logarithm function, I'm going to have a vertical asymptote. So the horizontal becomes the vertical. And what I also know about the asymptotes is if I had if I started with the horizontal asymptote was y is equal to a number, the vertical asymptote, should make that longer, the vertical asymptote will be x is equal to that number. So I'm just flipping the x and the y. So if I had, if I had y is equal to a number, and that was my equation for the horizontal asymptote, my logarithm, the inverse, would have x is equal to that same number as my vertical asymptote, the line I'm not touching. All right, so how do we convert between exponential and logarithm functions? Well, our exponential form, we're just going to focus on we're not going to do y is equal to a times b to the x power. We're just going to focus on the, like a parent function. So y is equal to just, actually I'm going to color code this. So I'm going to do y is equal to just b raised to the x power. We're just going to focus on that. If I wanted to write this exponential form in logarithm form, how I would convert the two, and we talked about this already. Actually, wait, sorry, we didn't talk about it already. I already made this video 3 times, so I talked about it. But I have y is equal to b to the x power. If I'm converting to logarithm form, I'm going to have the word log, base b, so I'm going to write the b like a subscript. I'm going to have y, it's like I'm doing of y, is equal to x. And then if I wanted to find the inverse, so if I wanted the inverse of this exponential form, I would take that x and y value and I would flip it. So I would write instead log base b of x is equal to y. And I meant to put that in blue. So something important, if this is the exponential form, this is the inverse. Let's do some examples with numbers. If I had y is equal to 2 to the x power as my base, my parent function that I'm talking about, I'm not going to convert that to logarithm form. I'm just going to talk about what's the inverse of that. So if I had y is equal to 2 to the x power, the inverse would be log base 2 of x is equal to y. And I could also write that as y is equal to log base 2 of x. I don't want to write that. I could write that as y is equal to log base 2 of x. That's the inverse of y is equal to 2 to the x power. If I had y is equal to 5 to the x power, the inverse would be y is equal to log base 5 of x. If I had y is equal to 7 to the x power, was my exponential form, the inverse of that would be y is equal to log base 7 of x. Okay. A way to help you remember this conversion, now so that's talking about inverses of the inverse of an exponential function. What's the logarithm inverse? Now we're going to focus back on converting between exponential form and logarithm form. So I have an easy way to remember this is let your y be your answer. Let a represent it. Let b be your base. It already is. Let b be your base, and then let e be your exponent, or what was x before. To convert between exponential functions and logarithm functions, I'm going to have log, the word log, the base b of a is equal to e. Logarithms are always going to spit out an exponent. They're always going to spit out the time, if you're talking about a word problem, or the exponent. They're spitting out an exponent. That's the output. How you can remember this, answer, base, exponent, those are easier to remember. If this is your exponential form, then this is going to be your logarithm if you convert to that form to logarithm form. So this is exponential form, this is logarithm form. I should write that. You can remember this because some people say that logarithms are difficult, so for the next few weeks while we're working with logarithms, you can remember that log has to come before anything else. So log is bay for the next few weeks while we work on logarithms. And that's how you can remember it, because you see B, A, E, the letters or the variables in that order. What this actually says, what this thing that looks weird actually says is, or what it actually asks, is to get from B to A. So to get from B to A, what exponent would I need to raise B to? So to get from B to A, that base to that answer, what exponent would I need to raise B to? That's what that actually asks, or what that function says. And important log info, so important information on logarithms that you should remember. The input is the answer. The input is the answer. That's what you're inputting into the logarithm. It's always going to be the biggest number. If you can't remember that, it's always going to be, that answer is always going to be the biggest number, aka the biggest number. That's what you're plugging into the logarithm. The output is the exponent. It's always going to be the exponent. That's what a logarithm spits out. Always. It spits out the exponent. All right, now we can revisit, now that we've talked about this and how to convert, we can revisit the problem, how many days before 7 billion people will be infected? We can find the inverse of our exponential form. So if we look back to our problem, our exponential form was y is equal to 10 to the x power. So let's put that. Wait till it loads because it's ridiculous. Come on, man. Please. Okay. We have exponential form was y is equal to 10 to the x power. We wanted to find the inverse of that. So we flipped our x and y values and we got x is equal to 10 to the y power. And then now that we know how to convert between exponential form and logarithm form, we're going to do that with what we have up here. We're going to flip. So we're going to end up with, that's going to get us y by itself. It's going to get us to solve for y. We're going to have log of base 10, or log base 10 of our answer, which is x, is equal to y. And there, we've gotten y by itself now. Now we have y by itself. With this new function, all we have to do to get the number of days it would take to get a certain number of zombies is plug in whatever value we're given for the number of zombies and see what we get. So I would, in this case, our new inverse x represents the population. And that is x is equal to, in this case, x is equal to 7 billion we want to solve for. So we're going to plug in, we'll have log base 10, we're taking it from here, that's our inverse function, log base 10 of 7 billion is what we're going to do. This in your calculator is just log. The log in your calculator is base 10. So we just have to write log of 7 billion in our calculator. It's a lot of zeros. Can you believe people are billionaires? That's crazy. Did you see how long it took me to write that number? All right, I have log is on your calculator. It's a button on your calculator. You click the log button, and then all you put in is 7 billion. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9 zeros after the 7. And you would get that it would take 9.845 days. And we said it was going to be in between 9 and 10, and it is. It's right in between those 2 days. So that's how many days it would take. We knew it was going to be between 9 and 10, and it is. The common logarithm is the log with base 10. You can write log base 10 of x as just log of x, which we just did. So you don't have to write the 10. If you have base 10, you don't have to write it. If you see a log with that, ow. My funny bone. If you see a log with no base, then you know that the base is 10. And that's the common logarithm. We're going to try to convert. We're going to practice converting between, because I know this is probably, you're like, what? Too many letters. So we're going to do it with numbers. We want to rewrite 25 is equal to 5 to the second power. This is an exponential function. We want to rewrite it in logarithmic form. We're going to identify what's our base. Our base is 5. We're going to identify our exponent. Our exponent is 2. And our answer is 25. And I'm going to just zoom this up a little bit so you can see my formula. It should be on your paper though, so you can see it there. I'm going to write, if this is my exponential form, my logarithm form will be log, so I have log base 5 of the answer 25 is equal to 2. It's spitting out the exponent. And that would be my answer. This would be the logarithmic form of that exponential form. If I did it with the second problem, I'm going to identify this is my answer, this is my base, this is my exponent, and all I'm going to do is I'm going to look at this conversion, or how I'm going to convert between the two, and I'm going to take I'm going to do log base 6, my base is 6, of 216, that's my answer, is equal to the exponent. The exponent here is 3. See, this isn't so bad, right? All right, let's try another one. If we have log base 3 of 9 is equal to 2 in exponential form, I'm going to identify, now I've been given the logarithmic form, I want to convert to exponential form. The base here is 3, it's the subscript. The answer is 9. The exponent is 2. So I know that I can write 3 to the second power is equal to 9. I know that statement is true. So I know that I've done this correctly. I should have wrote this in blue. The answer is 9. This is a correct statement, so I've done it correctly. If I had log base 2 of 64 is equal to 6, I know my base there is 2, my answer is 64, my exponent is 6. So I'm going to rewrite this in exponential form. I mean to take that base 2, raise it to the 6th power, and that should give me 64. And if you remember, that is correct. You can check it in your calculator, but this is a true statement, so I know I've converted correctly. What this logarithm is actually asking is, what power do I need to raise 2 to get 64? What power do I need to raise that base to get 64? 2 to the 6th power gives me 64. I want you to try these examples on your own. So pause the video and try those 4. All right, for the first problem, for 1/2 to the 3rd power is equal to 1/8. You're going to identify the 1/2 as your base, the 3 is your exponent, and the 1/8 is your answer. So to write this in logarithmic form, I'm writing the word log. The base is 1/2, so I'm writing that as a subscript. The answer is 1/8, so I'm writing that not as a subscript. But you usually see it in parentheses. In your calculator, it's going to put it in parentheses, that answer. And that's equal to, I have the exponent is 3. So here is my logarithm form of that exponential form. For the next one, I'm going to identify this is my base, this is my exponent, and this is my answer. And to write that in logarithm form, I'm going to have log, the word log, base 2 of the answer, which is 1/32. Make sure you write that 2 as a subscript, is equal to -5. It's spitting out an exponent, and it spit out the exponent here. What base do I need to raise 2 to get 1/32? And that is 5. So I could also think about it like this. 2 to the -5th power gives me 1/32. We're going to do that later. Don't worry about that. For rewriting log base 4 of 64 is equal to 3 in exponential form, I'm identifying this is my base, this is my answer, this is my exponent. The answer should always be the biggest number if you forget. So I'm writing this in exponential form. My base is 4, my exponent is 3. This is equal to the answer of 64, and that is correct. 4 to the 3rd power is 64, so I've done this correctly. Rewrite log base 7 of 49 is equal to 2. This is asking, what base do I have to raise 7 to get 49? And that base is 2. So 7 to the 2nd power gives me 49. I can write 7 to the 2nd power gives me 49. And that's the exponential form. I did this wrong. This should be green. 49. Done. let's try the next thing. So that's converting in between logarithms and exponential functions. I'm going to rewrite that. So how to convert between log form and exponential form. On top, just so we have it with us. And we don't have to look back to this other page. We have log base b of a is equal to our exponent. And the exponential form of that is the base b raised to the e power is equal to a. Another way that you can, when you're looking at the logarithm form, if you raise b to the e power, you're going to get the answer. So you can always think about it that way too. If you draw arrows going, what is that, counterclockwise or clockwise? Counterclockwise, b to the e power is going to give you a. B to the e power is going to give you a. So we can use this idea to solve for logs we already know. If I want to evaluate log base 8 of 64, this is saying, or what it's asking is to get from 8 to 64. What do I need to raise 8 to? What do I need to raise 8 to? And what I'm going to do, this one's an easy problem. I'm going to set this equation equal to e, because I know it's going to spit out an exponent. And I want to do 8 to the e power is going to give me 64. I know I have my base is 8. I'm raising that to the e power, and that's going to give me 64, which is my answer. What is e equal to? I can tell right off the bat. I know it's 2. I know you raise 8 to the second power to get 64. For this second one we have, evaluate log base 8 of 4. What this says is, what do I need to raise the base 8 to get 4? That's what it's asking. I'm going to set this equation equal to e. I know it's going to spit out e. I want to know 8 raised to what power gives me 4? My base is 8. I can convert to exponential form. I have 8 raised to, my exponent is e, is equal to, my answer is 4. Oh, wow, in this case, it's not the bigger number, so I lied to you. It's usually the bigger number. But in this case, our e is going to be a fraction. That's how it's going to be a smaller number. But if your exponent is a whole number, then your answer is going to be the biggest number. Okay, I have 8 to the e power is equal to 4. I don't off the bat know what that is, what power I need to raise 8 to get 4. So what I'm going to do in problems like this is I'm going to rewrite both sides with the same base. So on the left, instead of writing 8, I'm going to write 2 to the third power. I know 8 is 2 to the third power. So I have 2 to the third power, really. And let me color code this so you can tell what's going on. I have 2 to the third power instead of 8 raised to the e power. And on the right-hand side, I have 2 to the second power. And then what I actually have on the left, when I raise a power to a power, I'm multiplying those powers together. So I have 2 to the 3e power is equal to 2 to the second power. So I have 2 to the 3e power is the same as 2 to the second power. I know that those powers have to be the same. 3e has to be equal to 2. 3e has to be equal to 2. The powers have to be the same. Then I just solve for e. I divide both sides by 3, and I get that e is equal to 2/3. And that's my answer. For this next problem, I have log base 9 of 27. I want to evaluate that. I'm going to set this equal to e. And I want to know 9 raised to what power gives me 27. I can also think my base is 9. My exponent is e. I don't know what it is yet. And that's equal to my answer, which is 27, if I convert between logarithm form and exponential form. I can also think about the arrows if I want instead. I don't know what e is, so I'm going to need to calculate. I'm going to need to figure it out. I'm going to rewrite both sides in terms of the same base. 9 and 27 share a base in common. I should have specified that for the last problem. They share a base in common, and that base is 3. So you need to think about, what do the two sides share in common? What base? 9 and 27 share 3 in common. So if I raise 3 to the second power, that gives me 9. So I have 3 to the second power to the e power on the left-hand side, and on the right-hand side, if I rewrite 27 in terms of 3 to some power, I have 3 to the third power gives me 27. If I rewrite the left-hand side, I have 3 to the 2e power. When I raise a power to a power, I multiply, is equal to 3 to the third power. So with this, I know that 2e has to be equal to 3. 2e has to be equal to 3 for those two sides to be equal to each other. They have to have the same exponents. I'm going to divide 2 on both sides, and I'm going to find that e is equal to 3 over 2. For evaluate log of 100, if I don't see a base, remember that that base is 10. If I don't see a base, I know the base is 10. So what this is really asking is, well, I'm going to set this equal to e. This is asking, what power do I have to raise 10 to get 100? That's easy, but I'm going to rewrite this. 10 to the e power, if I write this in exponential form, is equal to my answer, which is 100. 10 was my base, e was my exponent, my answer is 100. E, I know, is 10. 10 to the 10th power gives me 100. Wait, oh my god, what? No. E is 2. E to the second power gives me 100. If I raise 10 to the second power, 10 times 10 gives me 100. Silly. For the next problem, I have evaluate log base 3 of 243. I'm setting this equal to e. I'm going to do 3. So 3 is my base. I'm writing it in exponential form. E is my exponent, and that's equal to my answer, which is 243. I have 3 to the e power is equal to 243. I know that 243, if I don't know that 3 to the 5th power is 243, I can figure that out using my calculator, but e in this case is going to be 5. So 3 to the 5th power gives me 243. If I want to evaluate log base 1/2 of 16, I'm going to set this equal to e. No, it's going to spit out an exponent. I'm just going to write that so I can see more clearly how to convert this. This base is 1/2. I'm raising it to the e power, and that's going to give me my answer, which is 16. I want to rewrite both sides. This is a little tricky because I have a fraction on the left-hand side. I'm going to put that in parentheses. That's being raised to the e power. I'm going to rewrite 1/2. 1/2 and 16 share a base in common, and that base is 2. I'm going to rewrite that fraction 1/2 as 2 to the negative first power. It's 2 to the negative first power raised to the e power in this case. And that's equal to, on the other side, I have 16 I can rewrite as 2 to the 4th power. On the left-hand side, I actually have 2 to the negative e power. Negative 1 times e is negative e in the exponent. And then on the right-hand side, I have 2 to the 4th power. So negative e has to be equal to 4, which means e has to be, negative 4, sorry. I multiply both sides by negative 1. And I get e is negative 4. For this one down here, I was given an equation. I know x plus 3 is my exponent. 4 is my base. 8 is my answer. I'm rewriting this as 4 to the x plus 3 power gives me my answer of 8. And then I want to solve for what x is. I'm going to rewrite these two sides in terms of the same base. 4 and 8 share a base in common. That base is 2, so I'm going to rewrite 4 as 2 squared. So I have 2 squared to the x plus 3 power. And on the right-hand side, I have 2 to the 3rd power gives me 8. If I multiply the powers together, 2 times x plus 3, I'm going to have 2 to the 2x plus 6 power is equal to 2 to the 3rd power. And I know that 2x plus 6 has to be equal to 3. So 2x plus 6 is equal to 3. I'm going to subtract 6 from both sides. Whoops. I'm going to subtract 6 from both sides. I'm going to get 2x is equal to negative 3. I'm going to divide both sides by 2, and I'm going to find that x is equal to negative 3 over 2. For the last one, I'm going to evaluate log base 3 of 81 is equal to x minus 2. I want you to try this one on your own, actually. So try that one on your own.